Hello there. You have probably heard of the liar paradox, which asks whether the statement, "this statement is false," is true or false. Of course, the paradox here is that if you say it's true, then the statement itself says it's false, and if you say it's false, that the statement correctly says it's false, making it true. This sort of self-referencing paradoxical statements can always be constructed quite easily in English. We are, however, not particularly concerned about these because we don't expect sentences in English to be either true or false. It, however, is not the case in logic. Now, in logic, a logical system is a set of axioms or facts which we have assumed to be true, and a set of derivation rules which allow us to find new true statements from the given axioms. Every statement in a logical system does indeed need to have a truth value. Now, if we could find a paradox as before inside the logical system, we would reach Gödel's Incompleteness Theorem, one of the most groundbreaking theorems from the 20th century, on par with Heisenberg's uncertainty principle or Einstein's theory of relativity in terms of groundbreakingness. It says in its most simplified and clickbaity version that math is incomplete. Now you may wonder, why are we worried about that? There are several incomplete things in life, and to answer that we must first talk about what it means to be complete in logic. A logical system is said to be complete if every true statement in it can be proved. So what the theorem says is, there are true statements in mathematics that cannot be proved. This is unsettling because since the time of the ancient Greeks, mathematicians have intuitively had the idea that any true statement must be provable. Of course, that proof might be difficult, or perhaps very, very difficult, but provable nevertheless. However, Gödel's Incompleteness Theorem says that the problems that you might have been working on for years might not actually be solvable at all despite being true. Now, coming back to the theorem itself, let's look at a less clickbaity version of the definition. In a sufficiently powerful, consistent logical system, there are statements that can neither be proved nor disproved. To start off, by sufficiently powerful we mean the logical system can carry out a certain amount of arithmetical operations, and by consistent we mean it is impossible to prove both a statement and its opposite in the logical system. For example, we can't prove both Earth is round and Earth is flat using a consistent logical system. To start off proving this, the first step is to encode every logical formula f as a natural number g of f, which Gödel referred to as Gödel numbering. The idea is to assign the natural number to each symbol and then build up statements by putting together the natural numbers associated with the symbols of that statement. This is quite similar to binary encoding that is used by computers everywhere. Now, with the natural number associated with every formula, we can define the properties of logical formulas using numbers. For example, we can have a function negation of x on numbers which sends x, which is a natural number, to the Gödel number of the negation of the logical formula associated with x. Another thing to note is we can determine using computer programs whether for two formulas f1 and f2, f1 is a proof of f2, since proofs in logic are basically just logical formulas themselves. Using this fact, we can have a function proof of x of y, which returns true if the formula associated with the number x proves the formula associated with the number y, given they are valid formulas. Now we can define provability of the logical formulas in the terms of natural numbers as a formula x is provable if there exists a logical formula y such that y proves x. So, provable of x can be defined as there exists y such that proof of y of x. Now remember that each logical formula is tied to a natural number by the Gödel numbering, so we can arrange all formulas which take one free variable as input in ascending order of its Gödel number. This way we create a list of logical formulas with one free variable such that every logical formula with one free variable is in that list. Again, they are functions over natural numbers. So not only are they indexed by natural numbers, they also take natural numbers as arguments. Now consider the formula D, where D of n is defined as not of provable of f sub n of n, which says that for D of n, if we take the nth logical formula from the list of formulas we created and see whether it's provable when given input n, the formula D of n returns true if it's not provable and false if it is. But since D itself is a logical formula which takes one input, it must be in the list above, let's say indexed by I, some natural number I. Then look at what happens if we replace the n in D of n with I. We obtain D of I equals to naught of provable of D of I. Then if D of I is provable, then D of I is false, meaning we just proved a wrong statement which cannot happen in a consistent logical system. So d of I must not be provable, which in turn would imply that d of I is true. Essentially, we have constructed a statement inside our logic which says that I am not provable. Thus, in our logic we have obtained true statements that cannot be proven. Hence, we conclude our proof.